Hi, I am Rishabh. I was a participant at the protocol study group and I am eager to participate in the Ethereum Protocol Fellowship program this year. In this video, I will be demonstrating the merkle-patricia-trie. So first I will be going through the workings of the Merkle tree, followed by the Patricia-trie. Then finally I will be demonstrating how we combine the features of the Merkle trees into the Patricia-trie to produce merkle-patricia-tries and what their benefits are. So a Merkle tree is a tree in which each node contains a hash value which is generated from combining all the hashes of its children nodes, and the leaf nodes which have no children, they contain the hashed values of the chunks of the data. So for example, consider here we had data ABCD, continuous data. So we split it into 4 chunks A, B, C and D, and after that the leaf nodes were assigned the hashed values of the original data chunks, and after that the every parent node stores the hash value which is generated by combining the children of that node. This continues until we reach the root. So the hash value at any node kind of represents the data in the entire subtree below it, and the hashing algorithm that Ethereum uses is KCAC 256. So what are the benefits of using the Merkle tree? So in the Merkle tree, since all the nodes contain some hashed values and the sizes of all hashes are fixed, so we can easily calculate the size of the entire tree by just knowing the number of leaf nodes. And also for checking the integrity of the data, we can just compare the hashes at the root nodes and verify whether the data is valid or not. So like in the Ethereum blockchain, the Merkle roots of 3 Merkle state trees are stored in each block header, in the block headers. So the state root, the transaction roots and the receipt roots. So we do not need to store the entire tree in the block. We can just fetch the root hash from a trusted source, and that would be enough to verify whether the data of the entire tree that we fetch from even an untrusted source is valid or not. I have prepared a demonstration of the Merkle tree here. So here, like we can see, I have given 3 different sentences as the data, and here for the chunking of the data I have split the data into 32 bit chunks, and as we can see, the first tree and the third tree have the same data, represent the same data, so their root hashes are the same, while the second tree has a different data, so its root hash is different. So the main problem that we face with Merkle trees is that it takes too much of space for storing the keys, as it is a tree. So both the key and values are stored inside of each node, and we use the keys to get to the nodes containing the value. But here we can use a better data structure like a trie, which stores the keys along the path that we traverse along the tree to reach the value, and we can further space optimize a trie to a more compressed version of the trie, which is the Patricia-trie, in which every parent that has a single child is merged with that child. So here on the left side we can see a trie in which we stored the words big, bigger, bill, good and goal, and on the right side we can see the equivalent Patricia-trie, which is more compressed and takes lesser space to represent the same data. So like I said, the main advantage of using the Patricia-trie over any kind of trees is that we can store the keys along the path, so it is more space optimized. I also have a demo for the Particia-trie using those same values that we saw earlier in the diagram. So by the way, these values that are printed for the trees are the level ordered traversals of the trees, and the level order traversal of the Particia-trie will also be displayed in this demo. Yeah, so this is the same thing that we saw earlier here. So finally we introduced the merkle-tree logic of each node containing the combined hash of its children into the Particia-trie to obtain the merkle-patricia-trie. This works like a Particia-trie in terms of the key. Here I have taken some 256-bit keys. Say these are the key value pairs in the data that we need to represent. The prefix tree of the keys has been created, and after that the hashes of the data are stored in the leaf nodes, and every intermediate node contains the combined hash of all of its children. So I have a demonstration for the same. So here for example I generated 3 256-bit hashes and 3 corresponding data I have taken. The 3 hashes I considered as the 3 accounts, and I created 3 merkle-patricia-tries. So the first and third trie both contain the key value pairs for user 1 and user 2, so their root hashes are similar, while the second trie contains the hashes of the key value pairs of users 1 and 3, due to which its merkle root hash will not be equal to that of trie 1. So here we can see the level order traversal of the 3 merkle-patricia-tries. The first and the third trie have the same root hash, which signifies that they contain the same data. So using the merkle-patricia-trie, we get the good sides of both the merkle trees and the Particia-trie. We can still verify the integrity of the data in O of 1 time by comparing the root hashes, and we can easily calculate the size, and we can also prove the presence of data in log n time, as well as it is more space optimized in comparison to the general merkle trees. So here is a link to the code for the demonstration that I just showed, and I also included some of the major references that I used for learning about the merkle-patricia-tries. I know that the official implementation of Ethereum uses some more steps, like the recursive length prefix before storing the hashes, but I have not included that here for the sake of simplicity. I also know that currently the research is going on for merkle trees. Thanks for watching. Thank you for your time, and I really hope I get selected.